Okay. We have two lines, L and M, and we have the vector equations written this way. How do they look that way? Yucky. Okay, so what I would probably do is rewrite these. Can you see that the point is 5, 3, and 0 plus S, negative 4, 1, and 2, and Rm, negative 3, 7, and 6. And our direction would be minus 4, minus 1, and 0. RL. Thought that looked like an L. There. Same L that you would use like in the natural log. Now, in 3 dimensions, these two lines cross. In 3 dimensions, these two lines cross, and where they cross, they have a point in common. It's a hard enough question in 2 dimensions when you had y equals mx plus b with 2 equations that things would cross and you'd find out where they crossed. If you remember solving those, you'd set up a system of equations and then solve for x and then solve for y. Sort of the same thing's going to happen here. We're going to set up a system of equations. We know from our first line that the x-coordinate is 5 minus 4s, our y-coordinate is 3 plus s, and our z-coordinate is 0 plus 2s. We know from our second line that our x-coordinate is negative 3 minus 4t, our y-coordinate is 7 minus t, and our z-coordinate is 6. Always 6. Now, in order for them to cross, they're going to have to be equal. So what we can set up is the x-coordinates would have to be equal, which would mean that 5 minus 4s would have to equal negative 3 minus 4t. Because if they have a common point, the x-coordinates would be the same. And same thing happens with the y-coordinates. Our 3 plus s would have to equal 7 minus t. And our z-coordinates would have to be the same. So 2s would have to equal 6. And we have to see with those 3 black equations, is there enough information to solve things? Yes. In fact, there's one that's really easy to solve for. You can see through the z-coordinate that s is really easy to solve for. According to this, we know that s has to equal 3. If s is equal to 3, and I'm going to just number these equations, equation 1, equation 2, equation 3. If I take equation 2 and I plug in s is equal to 3, then I'm going to get t is equal to 1. Let's just double check equation 1. If the left side and the right side are the same when we plug in s equals 3 and t equals 1. So if I plug in 5 minus 4 times 3 for the s, and I plug in negative 3 minus 4 times t is 1. 5 minus 12 is negative 7. Negative 3 minus 4 is negative 7. This works. So it is true that t is equal to 1 and s is equal to 3. That hasn't found the point that's in common. We just know that there are parameters that will make it work. Now, to figure out what the actual point is, you could either plug in s equals 3 into these ones, or you could plug in t equals 1 into these ones. Either way, you're going to get the same point. And that point is going to be 5 minus 12, negative 7. 3 plus s will be 6. And z is always 6. But even if you plug in s, you'll get 6 for that as well. And so negative 7, 6, 6 is the common point. Very typical question, finding the point in common, quite likely on a final exam. For sure on your test. Also quite popular is finding the angle between two vectors. No, it won't be 7 points. This will only be like 3 points in this class. So you got a three-dimensional vector and another three-dimensional vector. They cross at a certain point. So we've got our line L in 3 dimensions, and we've got our line M in 3 dimensions, and we know that they cross at a point, and we figured out that that point was negative 7, 6, 6, somewhere in 3 dimensions. And if you happen to take those 3 dimensions and look at it, you could say there's an angle between those two vectors. What is that angle? This is not the final answer. Theta. Call it theta. Now, according to one of our important results, we know that cos of theta is equal to the dot product between two vectors divided by the length of each of those vectors multiplied together. Which vectors do we choose? How can we best describe this vector L? We've got a vector equation for L. It's right here. But what would best describe the vector L? It's going to be this one. This is our direction vector. So along here for L, negative 4, 1, 2 is the direction that vector L is going in. And it doesn't matter how long or how short you make that vector, the angle between those two vectors will be the same. So we have a direction vector for L. We're going to also have to use our direction vector for M. Not the point on the graph. Negative 4, negative 1, 0. That would be, is it negative 1 or positive 1? Good. Negative 4, negative 1, 0. That'll be the direction vector for M. So to figure out what the angle is, cos of theta will equal the dot product between U and V. So that would be negative 4 times negative 4 would be 16. 1 times negative 1 would be negative 1. And 0 times 2 would be 0. Over the length of U will be the square root of 4 squared is negative 4 squared is 16 plus 1 plus 4. And our second one, negative 4 squared is 16, negative 1 squared is 1, 0 squared is 0. And so we have cos theta is 15 over root 21, root 17. Go to our calculator. Cos inverse of 15 divided by First of all, since cos of theta is a positive number, we knew it was going to be between 0 and 90 degrees. And when we did cos inverse, we get the angle to be 37.5 1.45 degrees. Yes. Yes, I can scroll up. Is that good?